So we're now going to build on those compound formulas and come up with the double angle formulas. And do think of them as double angle, not 2 theta. I mean, 2 theta is how we go and derive it, but it's any time you've got a double angle you can use it for. So sine 2 theta, well 2 theta is double theta. So I could rewrite that as sine theta plus theta, which of course we now know we can rewrite as sine cos, cos sine. If it's the sine, it's the sine. We have sine theta cos theta plus cos theta sine theta, which are of course the same thing. And we come up with the first of our double angle formulas. Sine 2 theta is 2 sine theta cos theta. Okay, cos. The double angle of 2 theta we can rewrite as theta plus theta. And this one we go cos cos, sine sine. If it's not the sine, it's not the sine. But that gives us cos squared minus sine squared. But of course we can rewrite this one because we've also got trig identities that involve cos squared and sine squared. So I could rewrite sine squared as 1 minus cos squared, and I end up with 2 cos squared minus 1. But how about we change the cos squared? Cos squared is 1 minus sine squared, and that becomes 1 minus 2 sine squared theta. Tan 2 theta then. Tan plus tan and 1 minus tan tan. So we get 2 tan theta and 1 minus tan squared theta. So they are our suite of double angles. Sine 2 theta is 2 sine theta cos theta. Cos 2 theta, cos squared minus sine squared, or 2 cos squared minus 1, which is handy because we can rewrite that to make cos squared the subject, and we get the cos squared theta as a half of 1 plus cos 2 theta. Is very useful, especially when it comes to integration, which we'll see. 1 minus 2 sine squared, also very useful. We can rewrite it as sine squared half 1 minus. So notice those two, cos squared and sine squared. One of them's plus cos 2 theta, one of them's minus cos 2 theta. So the plus goes with the cos, so it's the same. If you get some cos squared plus cos, sine squared minus cos. And tan 2 theta, there it is, 2 tan theta and 1 minus tan squared theta. So as I say, our double angle results. So if cos theta is 2/3, find the tan of 2 theta. Well, let's draw a triangle up. 2/3 is the cosine ratio, so opposite side there is root 5. So we can sub into our 2 tan theta 1 minus tan squared theta, tidying all that up. Eventually, there it is, minus 4 root 5. Find the exact value of sine 5 pi on 12 cos 5 pi on 12. Well, the trick there is to pick up the sine cos, because we've got a double angle result that says sine 2 theta is 2 sine cos. So this sine cos, if you like, I could think of it as a half of 2 sine cos. So it's going to be a half of sine 2, or double the angle, which will be 5 pi on 6. 5 pi on 6 sine, where are we? Second quadrant, aren't we? Acute angle is pi on 6, which is 30, half times a half, a quarter. You are correct. What about this one then? Cos theta is 2/3. Find the exact value of sine theta on 2. And this is where thinking as double angles comes in handy, because theta is double sine theta on 2. So I can still use the double angle results here. And that's where rewriting it as sine squared comes in handy, because I can now say, well, hang on, sine squared theta will be a half of 1 minus cos 2 theta. That's written in double angle form. So for our one, I'm going to say sine squared theta on 2 is a half of 1 minus cos theta. So double angle on the right hand side there. Sine theta on 2 is the one I want to find. They've told me cos theta is 2/3. So sine squared is 1 on 6. Therefore, sine theta on 2 is plus or minus 1 on root 6. So we can't narrow that one down because they've told me cos theta is 2/3. What's that tell me? Oh, well, cos theta could be in the first quadrant. Now, if I know that, fair enough, I can narrow it down, because if theta is in the first quadrant, then when I halve it, it's going to be in the first quadrant. It must be positive. But they haven't told me that. They've just said cos theta is 2/3. The other possibility, it might be in the fourth quadrant. Halve something in the fourth quadrant, where you're going to end up in the second quadrant, aren't you? And so cos would be negative. So, need more information to work out whether it's plus or minus. Prove this identity. The square root of 1 minus cos 2x on 1 plus cos 2x is the same as tan x. So on the left hand side I've got cos 2x. Now I've got 3 different ones I can substitute in. But I keep an eye on what I'm trying to prove. I'm trying to prove tan. Tan is, of course, sine on cos. So therefore, the result I'll use on the top would be the one that involves sine. The one I use on the bottom would be the one that involves cos. It makes sense. So we'll end up on the top with 1 minus 2 sine squared, and on the bottom we get 1 plus 2 cos squared minus 1. And we get some cancelling happening there. 2 sine squared on 2 cos squared, well the 2's obviously cancel. Sine squared on cos squared is tan squared. Square root of tan squared, we have our result that we're looking for, tan. Ah yes, quite an old question now, but it is a good one, because a lot of people wasted a lot of time on this question. Because you see they got sine 3 theta there. And so what a lot of people did is they said, oh, I need to come up with a formula for 3 theta. Oh, that's all right. I could rewrite that as 2 theta plus theta and then use the compound angle formula and so on. But if you did your algebraic fraction first, common denominator is sine theta cos theta. And look what you get on the top. Sine cos, cos sine. Now, we know when we have sine cos cos sine, how's it go again? So, if it is the sine, it is the sine. So therefore, the top of that I could rewrite as sine 3 theta minus theta. You'll notice I've also multiplied top and bottom by 2, because now, on the bottom of the fraction, I have 2 sine theta cos theta, which we would recognise as sine 2 theta. So on the top, you get 2 sine 2 theta. On sine 2 theta, bingo, it's 2. It's very quick. Had you come up with a formula for sine 3 theta and cos 3, it would have worked.
So you wasted time?
It wasted time, take a lot longer, yeah. Or an even older question. Prove 2 tan on 1 plus tan squared is sine 2a. 2 tan on 1 plus tan squared. What am I going to do with that? Well, 1 plus tan squared sec squared. It's tempting to change that one. But we need to get double angles in there somehow. I'm going to rewrite everything as sine on cos. So all those tans are going to become sine on cos. Ah, look what happens. Multiply top and bottom by cos squared. I end up with 2 sine a cos a, which we hopefully recognise. And on the bottom, cos squared plus sine squared. Wow, that's just 1. So there's our result, sine 2a. The sine of 2 times the inverse cos of 3/5. Remember, inverse trig, we're talking about an angle. So it's really saying the sine of 2 theta. Well, let's call it theta. Theta is the inverse cos of 3/5. Draw myself a triangle. So 3/5, other side then is 4. Oh, it's our classic 3, 4, 5. So sine 2 theta, 2 sine theta cos theta. And I'll just read off my triangle. 4/5 times 3/5 times 2, 24 and 25. Now this one's the other way round. The inverse cos of 2 cos pi on 3. I don't have a double angle result for inverse cos, so this could stump people until, of course, you realise, hang on, cos pi on 3, we know what that is. What is it? And 2 times a half, it's just 0. Voila. Okay, we'll do 17E, enjoy that.